Okay, so continuing on, we are going to take a look at what is the formula for the two-sample t-interval for the difference of two means, what are the conditions for this interval to be valid, and is this formula on the formula sheet. It's the same conditions as before in Chapter 9 for running a t-test. And the equation is the mean plus or minus the t-critical value times the standard error. So we find our t-critical value using our confidence interval as well as our degrees of freedom. You can either run it on the calculator or you can look it up in the table. For an example, we're going to look at Ashton and Olivia wanted to know if generic chocolate chip cookies have as many chocolate chips as brand name chocolate chip cookies. On average, to investigate, they randomly select 10 bags of Chips Ahoy cookies and 10 bags of Great Value cookies and randomly select one cookie from each bag. Then they carefully broke apart each cookie and counted the number of chocolate chips in each. Here are the results. Construct and interpret a 99% confidence interval for the difference in the mean number of chocolate chips in Chips Ahoy and Great Value cookies. So we have to state plan do. We want to estimate the difference between the Chips Ahoy and the Great Value cookies at the 99% confidence level, where mean sub CA is the true mean number of chocolate chips in Chips Ahoy cookies, and mu sub GB is the true mean value or mean number of chips in Great Value cookies. Our plan is if the conditions are met, we will calculate a two-sample t-interval for the difference of these two means. This is random because the data came from independent random samples. 10%. There are more than 100 Chips Ahoy cookies in circulation and more than 100 Great Value cookies. Because there is no obvious skewness or outliers in the graphs below, it is safe to use t-procedures. Now we had to do this graph because our sample size was not greater than 30. So unless your sample size is equal to or greater than 30, you have to go ahead and graph. We don't know that it's supposed to be normal for the shape, so we have to go ahead and look. And there doesn't seem to be any major skewness or outliers. So for these data, we have a mean of 18.4, a standard deviation of 1.78 for the Chips Ahoy cookies, and we have a mean of 19.4 and a standard deviation of 3.6 for the Great Value cookies. Now you would put this in your calculator, both of these lists, individually calculate your mean and your standard deviation using the calculator so you don't have to be bogged down with the formulas. We're going to find our degrees of freedom by taking 10 minus 1 and the critical value for 99% confident interval, and we plug that into our calculator to determine what our t-value is going to be. We then go ahead and plug it all into our interval equation. We're going to do the difference of the means plus or minus our 3.25 for our t-critical, divided by or multiplied by our standard error. And then when you actually work that out, you get that our confidence interval is from negative 5.127 to 3.127. You can also do this in the calculator. Two sample t interval, you're going to put in list 1 and list 2. Our frequencies are both 1. The confidence level is 0.99. Again, our data is not pooled, and it would go ahead and give us these for our interval and our degrees of freedom. Now remember, there's a crazy equation that the calculator uses for degrees of freedom, so it is different than our more conservative option. So now we want to make a conclusion. We are 99% confident that the interval from negative 4.814 to 2.814 captures the true difference in the mean number of chocolate chips in Chips Ahoy and Great Value cookies. Does your interval provide convincing evidence that there is a difference in the mean number of chocolate chips? Because the interval includes 0, there is not convincing evidence that there is a difference in the mean number of chocolate chips in Chips Ahoy and Great Value chocolate chip cookies. So this negative is saying that we went ahead and subtracted, let's go back and look, our mean had Chips Ahoy minus Great Value. If this is greater than 0, that means Chips Ahoy has more chocolate chips than Great Value. If this becomes negative, then that means Great Value has more chocolate chips than Chips Ahoy. If we look at the interval that we came up with, we have both negative and positive options. So Chips Ahoy could be more, Great Value could be more, we don't really know. But the other thing is that 0 is included in there. And because we are 99% confident that this interval captures the true mean, 0 is definitely an option. And if 0 is an option, they could be exactly the same. So there is not enough convincing evidence to deter that there is a difference in the mean number of chocolate chips. When doing two sample t procedures, should we pool the data to estimate a common standard deviation? Is there any benefit? Are there any risks? Do not pool ever. Pooling assumes that two populations have the same variance and that the population distributions are exactly normal. In the real world, this does not occur. Distributions are not exactly normal. The population variances are not exactly equal. Just don't pool. The benefits to pooling are that we have more degrees of freedom. We can do n-2, which leads to a narrower confidence interval and smaller p-values. However, this is only when population variances are equal and population distributions are exactly normal. But this is rarely ever the case. So the lesson for the day, don't pool. Always choose no. What about a two-sample test for a difference in proportions? Why do we pool for this test? So this is what we learned in 10.1. We pool for proportions because we need a way to estimate p. We don't have to worry about that with means. Should you use two sample t procedures with paired data? Why not? How can you know which procedure to use? We do not use two sample t procedures on paired data, and this is why. Would the test be messed up if the data were scrambled in the lists? If the answer is yes, then the data was paired, and you should be using the differences. And like we just said, when we use the differences, we do not pool. When determining your procedure, pay attention to the context of the problem. It is going to indicate what procedure you want to use. Our last example here, testing with distractions. Suppose you are designing an experiment to determine if students perform better on tests when there are no distractions, such as the teacher talking on the phone. You have access to 2 classrooms and 30 volunteers who are willing to participate in your experiment. Design an experiment so that a 2-sample t-test would be the appropriate inference method. So I'm going to say that maybe on 15 index cards we write A, and on 15 index cards we write B. We'll shuffle the cards and hand them out at random to the 30 volunteers. All 30 subjects will take the same reading comprehension test. Subjects who received card A will go to the classroom with no distractions, and subjects who receive B will go to the classroom that will have the proctor talking on the phone during the test. At the end of the experiment, we'll compare the mean score for subjects in room A with the mean score for subjects in room B. Now your random assignment could look different. Maybe you numbered the volunteers 1 through 30, and then you used a random number generator. If they got an even number, they went to A. If they got an odd number, they went to B. Maybe you flipped a quarter. There's a few different ways. The answers will vary for this type of question. The big thing is you have to make sure that you have randomly assigned each of the 30 volunteers, and you need to make sure that it is set in stone that which ones are going to receive which treatment. So using the same procedure in Part A, we're going to divide the subjects into 2 rooms and give them the same reading comprehension test. One room with distraction free, and the other will have a proctor talking on the phone. Then after a short break, we'll give all 30 subjects a similar reading comprehension test, but have the distraction in the opposite room. At the end of the experiment, calculate the difference in the 2 reading comprehension scores for each subject and compare the mean difference with 0. So this would be our paired t-test. If we're allowing both groups to be given the same treatments, then we are going to pair the data. We'll be able to see what happened in each room when there was a distraction. Which experimental design is better? The experimental design in Part B is better since it eliminates an important source of variability, the reading comprehension skills of the individual subjects, which gives us more power. So because we allowed both groups to be provided with the treatment of having a distraction, we take away the fact that we don't know who got assigned to which room, and we don't know how good they are at reading. What is the purpose of random assignment in this experiment? To make sure one treatment isn't favored by always going first or second. So there is a little bit of random assignment in that sense, is that we had room A has the treatment of distraction first, and then room B gets it second. So there could be some variability in that. That's it. Tomorrow we will have plenty of time to work on Math Excel.